What's going on, YouTube? Mudduck Sharky, and this is part 2 of my LDMOS mobile power supply. So, I spent some time messing with these today and learning quite a bit about their operation. So, I, throughout this project, have been a little unsatisfied with the performance and just the general operation of how these modules work. So, they work great under some circumstances, and those circumstances are meeting the minimum voltage requirements and not drawing too much current. So aside from that, there's also some other things that I'm not fond of. One of them being that the current measurement is on the ground, on the negative side of the supply, which means that the ground going in and the ground going out need to be isolated from each other in order for the current limiting to work properly. There's no measurement on the input side for overcurrent protection. There's no overcurrent protection on the input side, as far as I can tell. Well, there sort of is. I'm going to show you that here in a minute. Another problem is that these draw a lot of current when there's no load. So these draw about 90 milliamps, 100 milliamps a piece when there's no load on them. So if I'm going to use this in a mobile and have 15 of them, I'm going to be drawing an amp to an amp and a half just having this thing plugged in with no load on it. Now that's kind of a problem. There's no easy way to turn this on and off. There's no easy connection to turn this on and off remotely other than simply unplugging it. And when we're dealing with 15 of these, that's up to like 400 and 450 amps going in, so we can't just put in a relay and shut the whole unit off. We have to shut it off at the board level. So I figured out how to do that. I figured out how to work around most of these issues. But the fact that I have to do that is kind of a pain in the butt. And these modules really aren't ideal for what I'm trying to do. But that said, I figured out how to get them to do what I want them to. So I was on a phone call today with somebody that's messed with these before and it's done something similar to what I'm trying to do. And he didn't have much success. So if you saw my previous video, I blew a few of these up, and that's because I blew them up because the output current wasn't balancing properly. So basically, by grounding the input and output together, I disabled the current limiting, and by not having them properly balanced, some of them drew too much current. So basically, one drew too much current, popped the fuse, and then the others had to pick up the slack, so one of those drew too much current, popped a fuse, and it cascaded down the line like that. And that's what led to the failure in my system, but I also found another failure mode. So if you're running these in a vehicle, your voltage is going to be probably unless you have something special like a custom alternator and voltage regulator, your maximum voltage is going to be 14.4. So if you try and draw a bunch of current and your voltage starts sagging at the input to these, what's going to happen is that the low input voltage is going to trigger. So these, let me grab a pointing device. So these have 3 potentiometers on them. This one up here in the upper right hand corner, that one sets your voltage on the output. This one sets your current limiting, but in my application I've disabled that. And then this one sets your low voltage protection. So if your voltage on the input drops below a certain level, this potentiometer adjusts that level, it's going to shut the module off, and then this little light right here is going to come on. So the problem is that no matter how precisely you adjust these potentiometers, if you have multiple units in parallel, they're never going to trigger low voltage at the same time. So another problem is that basically the minimum input voltage to these units is going to be about 11 volts. And I'll explain why that is a little bit later. But for all intents and purposes, the minimum input voltage is going to be 11 volts unless you do some modification. Now, as I mentioned earlier, I want to have the ability to turn these on and off remotely. So I figured out how to do that, and I also figured out how to get around the 11 volt minimum input problem. So in a mobile, if you happen to be using these while your alternator's not running and you're on battery power, or you're on battery power and your batteries drain a little bit, and you get to the point where you're pushing 11 volts, 10 volts, maybe even 9 volts on here, you're going to have more issues than just this voltage limit. So you can crank this all the way down to like 6 volts. But the problem is there's certain components on here that aren't going to operate properly if you do that. Alright, so you may have noticed I have one over here that's had most of the parts removed. This used to be one of these versions, so there's 2 versions of this module that I'm aware of, and they're basically the same module with a couple of slight differences. So as far as I can tell, these 2 modules are almost identical, aside from a heatsink on this IC right here, the size of the inductor cores, the size of the heatsink down here. So this one's got a small heatsink, this one's got a larger heatsink, and this one comes with a fan. The fan on this one happens to be removed. So this one is supposed to be a maximum of 20 amps going in. This one is supposed to be a maximum of 30 amps going in. So this one's got a 30 amp fuse, 30 amps worth of fuse. This one's got 40 amps worth of fuse. Aside from those differences, they're basically the same. As far as I can tell, it's all the same components that are used, aside from what I mentioned. Same values. There was one spot in here where there's a capacitor that's on this board but not on this board. But the overall structure is the same, and the modifications I'm going to show you should work flawlessly for both of these modules. So before I explain the modifications, I need to explain the basic structure of what's going on this board. So this is a pretty standard format boost converter. So the way that the switching MOSFET, the inductor, the capacitors, a couple of diodes under there, the way that's arranged is it's pretty standard stuff. I'm not going to go into the details on that, but I am going to say that basically this whole area, including the inductor and the capacitors, that's kind of your switching section. So that controls all the big power, and your inductor boosts the voltage up to get you to a higher point. The capacitors smooth it out on the output and on the input. What's under this heatsink is what controls the boosting action. So this is basically the switching supply control under here. Everything over here is just big power components, but everything under here is your switching supply control. So this is kind of like the brain of the device. That one being under a heatsink, this one isn't. So you can see over here, this IC and most of these components surrounding it, that controls your switching on and off to boost the voltage. So there's a couple components on here that don't control the switching, and that would be this IC and this IC. So what this IC is this is its own separate switching regulator. So if we look over here, this one's been removed, but the IC that goes right here is its own little switching regulator. Let's take a look at the data sheet. So this is it here. It's basically an almost self-contained buck converter, DC to DC buck converter. So this IC is capable of lowering the voltage, being a buck converter, but it's not capable of boosting the voltage. So that IC works in conjunction with this inductor here. I guess I better show you the components. This diode, this inductor, this capacitor, and that IC, those are the main components of that voltage regulator there. So basically what that does is it steps the voltage down from whatever you're putting in into something that can allow this IC and this IC to function properly. So this module is good for, I think it's up to 80 volts on the input. And obviously that would blow this IC, that IC. So this just steps that voltage down into something that these can handle. So this module and this module, they were clearly designed to have a fairly high voltage input. Well, working with these in a mobile, we're on the bottom end of that voltage. We're on the very, very bottom end. We're at 14.4 volts and the minimum is about 11. So there's a workaround here. Basically my modification allows this device to work down to very, very low voltages. And basically what we're going to do, and what I have done and tested it, is, so think about it this way. If you've got 10 volts coming in here, this can't possibly put out any more than 10 volts. So actually this little switching regulator right here drops about a volt. So if you're putting 10 volts in, it can put out a maximum of about 9. And the reason that is a problem is because of the switching MOSFET that controls the entire device. That's the main power switching MOSFET that boosts your voltage. So this MOSFET goes on the bottom of the board here. In between the board and the heatsink, you can kind of see it in there. But that's the one that does all of the switching that boosts your voltage. And the problem is that this is not a logic level FET. This is a 10 volt minimum. So if you put any less than 10 volts on the gate of this MOSFET, it's not going to fully turn on, and it's going to dissipate a lot of power. So that's what happens when your voltage starts to drop. So let's say you put 9 volts in and you turn the low voltage detection circuit. Say you turn that all the way down, so you can put whatever voltage in and it'll run. Say you put 9 volts in. Well, this is only going to be putting out 8 volts, so the gate on your MOSFET's only going to be seeing 8 volts, and it's not going to switch efficiently. It's going to dissipate a lot of power, and it's not going to fully turn on. So I have the data sheet for that. It's Super China. Everything on these modules is Super China. So 6.3 milliohms typical for our on resistance at a gate to source voltage of 10 volts. So if we start going lower than that, we're kind of pushing our luck, and this device is going to become very inefficient, and it might even blow the MOSFET. Without exceeding the rated input current, we might be able to blow that just by not turning on the gate all the way. So the way that we get around that issue is by completely removing this circuit. So this is my idea. This is how I'm going to solve this problem in my switching power supply with the 15 units in it. I'm going to remove this circuit, this little IC. I'm going to completely remove that out of all of these switching modules, and I'm going to supply the voltage that these need. I'm going to supply that externally and separately with an external power supply. I have it here somewhere. There it is. So this is what I'm going to do. I have this Meanwell switcher, and basically what it is, it's an isolated module. So you put 12 volts in, it gives you 12 volts out, but isolated. Now it happens to be adjustable, and it has a pretty wide range. So these boards, this little switching regulator right here, if you give it enough voltage on the input, this will put out 13.8 volts. So I'm assuming that that's what they designed all this to operate at, is 13.8 volts. That makes sense from the sense that most MOSFETs, you want to give them 15 volts to turn them on and off. But I think they kind of just split the difference at 13.8. So this is putting out 13.8. What I'm going to do is I'm going to completely remove that chip, and I'm going to feed power from this, because this is able to operate. I tested it. It's able to operate way below 9 volts. So in the event that my battery voltage were to sag momentarily below 9 volts, this would still be able to maintain a 13.8 volt output to keep this switching regulator working properly. It's not going to shut off. It's not going to fail. So if this were to fail on one of the modules, that could cascade down to other modules and start blowing them as well. Because if one blows, then everything else is taking too much current, and then something's going to blow, and it just cascades all the way down the line. It's an unfortunate problem to have to solve, no current balancing and all that stuff. These were clearly not designed for this, but we're going to make them work anyway. So the way to do this modification is best shown on this board. So that switching regulator used to be right here. Basically all that needs to be done is you need to desolder that from the board. Unfortunately, it's got the bottom of the IC is soldered to the board as like a heat sink, so these are pretty tough to remove. You may be able to cut one side, because all the way on the left here, these pads, these are all positive voltage in. So if you were to take a razor blade and cut all of those, you were to cut all those pins off of the circuit right here. If you were to go and you were to cut all of these right here, you would basically disable the input voltage, and this would just be sitting there doing nothing. So that's what you want to do. You either want to remove it or remove power from the input side. Now looking closer, hopefully this will focus. If you notice, there's a trace right there that's got a little bit of the red coating scraped off of it. That's the output of this IC. So if we remove this IC and then bring 13.8 volts into here, this whole board is going to operate normally. It's going to operate just fine. So there's another way that you can kind of go about this. You don't have to necessarily solder the wire directly to this point. Focus. So that output actually comes over here to this terminal right here. So we could solder our 13.8 volt input to this point right here that says RV1. But the problem with that is you can't get to it. It's hidden in there. It's almost impossible to get in there and solder a wire, thanks to this cheap Chinese engineering. You know, they just stuff the damn things in there any which way they please. So that's basically the modification. So that allows this whole module to operate below 11 volts without a whole lot of repercussions. One of the big problems with that is, you know, if you want 65 volts out and 5 amps out, if you want a certain amount of wattage out, you're going to have to derate that if you anticipate going below 11 volts or whatever your intended design goal is going to be. So my design goal is going to be 5 amps out at 65 volts. That's a lot of wattage. So if I want to put in less than, I don't know, 12 or 13 volts on the input, I'm going to have to derate that output. I'm going to have to sacrifice a little bit of output to work at a lower voltage. So I'm just planning for the worst, and just in case my voltage were to sag down to the 9 volt range, 8 volt range, I want these devices to function. It's okay if they get a little bit warmer, because that's not going to be a continuous thing. I'm not going to sit there and run this thing at 9 volts. If it just so happens to dip for a little bit, I want these to survive, and I don't even want to know anything went wrong. You know what I mean? So doing that modification allows you to do that. It's going to be kind of a pain. I'm going to have to run a wire from every one of these over to my external switching supply. But that's what you got to do. That's what I got to do anyway to get these things working properly. So another problem that this solves is having a remote turnoff. So the cool thing is that wire that we're going to run there to operate this switching regulator, if we just disconnect power from that wire, it shuts the module off. Boom. Problem solved. Now there is a caveat to that though. And the caveat is let's say you have 15 volts going in here and you shut all this off. There's still a straight through path that allows that 15 volts to come out the other side. So these terminals, by doing that, even if we shut these off, these terminals are always going to see whatever voltage is coming here at a minimum. And that's thanks to the design. Basically, what's going on here is this positive voltage is coming in, going to these capacitors, going straight through this inductor, and then straight out. I mean, it goes through a couple of diodes, but basically it just straight through. And when this turns on, a MOSFET pulls this inductor to ground, the inductor fluxes, and when the MOSFET releases, that flux collapses back and induces a higher voltage, and that's how you get your boosting action. But that's you know, power supply theory, and I'm not going to go too much into that because it's not my forte. But anyway, that's kind of where I'm at right now. So I know this has been a long video. If you're with me, that's awesome. I'm glad you watched this whole video, because that means there's somebody else out there that's just as nerdy about this crap as I am. But anyway, that about describes it. So in my next video, I'm going to put all these things together. This is turning into a 3-part series, which sucks. But in my next video, I'm going to put all these things together, put it into action, and see what happens. I think it's I think it's going to be good. But anyway, I'm Lead Duck Sharky, and I'm back out for now. I guess I might as well show that the modification does work. So over here, we've got 13.8 volts going in, and that's the control voltage. So 13.8 is operating the system. That's coming from this power supply. And this power supply is going into the board and being boosted up to 65 volts. It looks like 3.8 is kind of the minimum to get 65 out. And it works fine at higher voltages. I'm shocked that it's going all the way down to 3.8. If you go any lower, the output voltage starts dropping off. It's like it's trying to maintain it, but it just can't. I have no idea how this is going to handle 5 volts under load, because right now I've just got a small resistor on there, acting as like a 12K resistor, just taking a few milliamps of current. And I don't know if this is going to handle 5 volts very well under load. I'm going to have to test that one of these days. But for now, you know, just for little intermittent failures down, or intermittent dips down to 9 volts or so, I'm probably not going to be any lower than 10, but, you know, pray for the best, prepare for the worst. Little intermittent dips down to 9, I think it'll be just fine. But anyway, just thought I'd add that onto the video.